Okay, first up, we have Barton, coded computation and optimization in the cloud.
Hi, my name is Barton. I'm a PhD student in EE with Professor Mert Pilanji. At my poster, I'll be presenting how we use tools from coding theory to speed up computations and optimization in distributed computing. In the first part of the work, we're interested in speeding up distributed matrix vector multiplication, adding redundancy to computations to make the overall task robust against the slower compute nodes. And we're proposing a mechanism based on polar codes, and we're exploring how it improves over other coded and uncoded approaches. And in the second part of the work, we're interested in speeding up distributed zeroth order optimization. A practical application for this is the problem of adversarial attacks to deep neural networks based on zeroth order optimization. And come see my poster if you're interested. Thanks so much.
Thank you. Next up, we have Govinda Kamath, adaptive Monte Carlo optimization.
So I'm talking about adaptive Monte Carlo optimization, which is a method to speed up common machine learning tasks. One example would be something like k-nearest neighbors. So just to recap, this is like you have a bunch of images and say n images living in d dimensions, and you have a new image coming in. You want to find the closest neighbor to this image, and this is a very common task. So if you are doing this naively, you compute distances between this new image to all the images that existed before, and this is like an order nd task. So this, and when we are talking about images in like thousands of dimensions, this d becomes important, and you can do random sampling, which gives you some benefit, some improvement, but is still approximate and is often not right. So what we propose is an adaptive way where you try to look at you compute compute different amount of use different number of coordinates for different images to be able to narrow down candidates and do more computations on more promising candidates. So this is essentially our idea. In this case, we can reduce this from order nd to something like order n log n type-ish. And in practice, this gives us 100x improvement. This can be extended to other problems like k-means and clustering.
Thank you. Next up, we have Grayson Zuloff, air core coils for megahertz frequency wireless power.
Hi, thank you for having me. Ours is a bit different because we do power electronics, not computing, but I did notice the giveaway is a wireless power coil, so it's not too unrelated. Many of you have probably recently heard of Apple's wireless power product being canceled, and our goal is to make wireless power systems more efficient. So as you shrink the coils down, you don't have the problems that they had, like overheating and issues with electromagnetic interference. So what we're doing is we're optimizing the cross-section of the coils, 3D printing them, and then plating them with copper. And the goal is to make the quality factor, which determines the efficiency of your system, significantly higher. So I'd love, if you're interested in wireless power or power electronics in general, love to have you come by my poster and we can talk about wireless power for computing devices.
Thank you. Next up, we have Ginny Scarda, system-level analysis for optical interconnect specifications.
Okay, thank you. So the kind of problem we're looking at here is that if you're talking about large compute systems, so for example, the system we're looking at is 64 cores, we find that the bulk of the energy that's consumed is actually consumed by the processor while it's waiting for the result of a memory access. And this is due to the high latency of electronic interconnects. So kind of the two key questions that we're trying to answer here is one, how do reductions in the latency and energy per bit of interconnects actually translate to system level benefits? And we're answering that by kind of sweeping over energy per bit and latency values, and looking at what kind of energy delay product benefits we get over the system if they have the parameters for electrical interconnects. And we're interested in this because this kind of tells us how good we have to make these interconnects before we get appreciable system level benefits. And then the second question is, how can we actually achieve these sorts of reductions that will give us appreciable system level benefits? And one potential solution that we're looking at here is optical interconnects. And it seems like with the types of parameters that can be achieved using these sort of systems, we can achieve system level benefits of 4x and upwards. Yeah, so come by if you're interested in interconnects.
Thank you. Next up, we have Jonathan Timchek, harnessing noise and disorder to rescue optimal predictive coding from transmission delays.
It's quite a title. So we're in the Silicon Valley, and we're a bunch of computer engineers. And one of the things we spend a lot of time doing is eliminating noise in systems. For example, an accidental bit flip can cause a computer error. But then we look at natural computing devices like the brain, and we see that it's full of neuronal noise, full of disordered connectivity. And you have to wonder, is it because of a biological hardware limitation, or perhaps the brain's choosing this mode of computation on purpose? So I study this question in spiking neural networks. And here's an example on the slide. You can see this animated GIF. And the idea is you see the noise being varied from less noise to more noise. And then you see the spiking neural network trying to read out a signal. The signal is in blue, and the spiking neural network readout is in orange. And you can see that the signal readout is very messy when there's a lot of noise, but it's also very messy when there's very little noise. And so this implies that there is actually an intermediate value of noise that is optimal. You might be familiar with the term stochastic resonance for this kind of phenomenon. So if you're interested to learn more about this and how to actually calculate the optimal noise level, stop by my poster. Thank you.
Next up, we have Lin Xiao Mehta, grasp, learning to grasp with end-fingered robotic hands.
Thank you. To achieve successful grasp, gripper attributes including geometries and kinematics plays a role equally important as object geometries. We propose a meta grasp, a data-driven grasping synthesis method that not only considers the object geometries, but also the gripper attributes as the input. Meta grasp is built based on neural network, which is able to select the set of contact points, which are in false closure and are reachable by the robot hand. By using the contact point as the output, we are able to transfer between a diverse set of n-finger robot hands. We show in quantitative simulation experiments that our model is able to predict the validated contact point for 2 and 3 robot grippers. In real-world experiment, we also show that our model is able to predict the validated grasp on novel objects using a novel gripper without actual retraining. If you are interested, please come to my poster. Thank you.
Thank you. Next up, we have Logan Su, computational nanophotonic optimization with spins.
Hi. Photonics plays key roles in a wide variety of applications, ranging from optical interconnects and data centers to AR and VR to imaging applications. With the next generation of optical photonic, the next generation of these applications, they're going to require optics and photonics that are more efficient, more compact, and have new functionalities. Now, traditional photonics design is largely driven by semi-analytical formulas and hand-tuned parameters. And what we have found in our lab is that if you take the human out of the loop, you can get actually devices that are much, much more efficient. So as you can see from the slides, by using something we call adjoint optimization, we get devices that are very non-intuitive and not something that humans would simply would not come up with. We have validated this approach by experimentally fabricating and measuring these devices, and we strongly believe this is going to be the future of photonic design. Thank you.
Michael Bao, high-quality facial capture using anatomical muscle simulation.
So my name is Michael Bao. I'm invited by Ron Fedko. If you were here last year, I presented this topic, but now we have results and it's been accepted to CVPR. So if you want to come talk to me about using muscle simulation to target faces for high quality facial capture, so think visual effects, think digital faces in Star Wars and your Avengers movies, please come talk to me. Muscles are cool, and yeah, thank you.
Thanks. Michelle Lee, making sense of vision and touch, self-supervised learning of multimodal representations for contact-rich tasks.
Hi, everyone. I'm Michelle, and I'm presenting my work on multimodal representation for contact-rich task. This paper was recently nominated for Best Paper at the International Conference of Robotics and Automation. I'm excited to present the work to you today. So, as humans, we're able to seamlessly combine our sense of touch and our sense of vision when we're doing even just very simple tasks like putting a key into a keyhole. But this is actually quite difficult for a robot to do. So my research is thinking about how we can combine these very different modalities. To do that, we first learn a self-supervised multimodal representation, which just means that we don't need supervised labeled data. The robot can get the data itself and label it. And we learn a representation that fuses the different modalities. From there, we use deep reinforcement learning to learn a robust manipulation policy that works for many different kinds of peg shapes and geometries. If you want to learn more about my work, please come to my poster. Thank you.
Thank you. Mike Wu, zero-shot learning for code education, rubric sampling with deep learning inference.
So this is a project that's trying to apply machine learning to online education. So online courses like Code Academy have really great content, but they don't do a good job of giving feedback to help students learn. And that's mainly because feedback is really not scalable. Getting labels is super expensive, and students have an exponential number of ways to solve the same actual problem. So what can we do? Well, it turns out that teachers have a really good mental model of how students think and learn. So if we can distill that knowledge into a simple generative model like a grammar, then we can sample infinitely from that and create a data set that we can use to train your favorite deep net. So this turns out to work pretty well. We triple the previous state of the art, and we can actually highlight parts in the code that correspond to particular mistakes that students learn. So thanks.
Tian Li, unsupervised visual motor control through distributional planning networks.
Hi, everyone. The goal of this work is to enable autonomous robot learning without specifying reward functions in a manual fashion. Our approach is to learn an unsupervised latent space under which the robot can measure its progress toward the goal itself. Here's an overview of our approach. We first collect a large number of random physical interactions. Then using this random data set, we can train our model, DPN. We can use the goal metric produced by DPN to train autonomous reinforcement learning policies to complete tasks. So here's our result. Based on the goal image on the left, the learned reinforcement learning policy can complete this pushing task itself. So for more details, please come to my post session. Thanks.
We have Zheng Gang, data-driven cloth for e-commerce. Not yours.
Hi, everyone. So one of the challenges for companies that are trying to provide online cloud shopping is that the customers somehow establish unrealistic expectations of the garments look on their body by just looking at the 2D images on the website, so which introduce the logistical costs in returns, shipping, and restocking. So our lab is traditionally famous for computer graphics and making special effects for movies. We are now working on combining graphics, vision, and machine learning techniques to produce e-commerce applications with faster turnaround and good scalability. So here are some initial results. Given some post parameters, we are able to use convolutional neural network to produce the garment geometry with some decent amount of details.